Hello, Tensor friends. I had intended to use this proof in a problem of the day, but it turned out to be just too wacky. There's too much trickeration in it. There's some identities that are not well known. Uh, we'll see as we go. So I'm just going to present this because I worked really hard on this. It's a pain in the arse. And it's a good thing to see. I don't know how useful it's going to be, but you've seen this. I'm going to think from calculus 3, this identity, which you can prove by just using all of the components, right? If you want to. Well, this is a proof that is in most textbooks, and I went through it in great detail, and I'm really unhappy with this. I'll show you why as we go. Okay, so we have this cross product here, B cross C. So let's define a new vector D as B cross C, which that B cross C is a vector, yes? Okay. So if we write D as its linear combination and B and C as their linear combinations, the first thing they do is they pick this off. So they say the ith component of D is equal to the Levi-Civita permutation times these two components. Now, I consider this trickeration number one because this is not obvious. You would do this, and if you don't do this, the proof, you can't do it. I've tried to leave it the way it's supposed to be. You can't do it. Okay, so that's problem number one. Okay, so we said D is B cross C, right? So now we want to cross this with that. We're going to call that a new vector G. So it's A cross D. And so the component of G, GM, would be once again the Levi-Civita times the component times this component, the component of A and the component of D. And since we have an expression for D, the ith component of D, we could put that right back in here. Okay? And we get this. Now, these are vector components, so we can move them around however we wish. And let's move these to the beginning. All right? Now, let's break these out and look at them for a second. We want to permute these indices. Okay? So here is the first one. If I move I one time, that's an odd permutation. I get a negative min. If I move it two times, it goes back to positive, and I get imn. So this one is equal to that one. So let's put this one back in here. All right, so we rewrite it like this. Now here comes trickeration number two. One of my books actually states, using the well-known identity, you know you're in trouble when you see this, or it is obvious that. That's the same statement. That these two permutations to multiply together gives you this. Okay, that is not well known to me. I doubt it's well known to very many people. But if you don't have this, you're not going to solve this. So that's the part. Another part I don't like. And I had to prove to myself that this is true. So this is the pattern we've been using. All right. So let's write it out as it is, and we'll start here. See, I equals I. So we'll start with 1. All right. So we're going to go 1, 2, 3. So that's 1, 2, 3. Now over here we start with 1 because I is I. Go 1, 3, 2. 1, 3, 2. Okay. Now, okay, so J in this case is equal to 3. M is equal to 2. K is equal to 2. N is equal to 3. Over here, K is equal to 2. M is equal to 2. J is equal to 3. And N is equal to 3. Okay, so this is a positive 1 times a negative 1 gives what? A negative 1. Now, what's this and this? Well, the Kronecker delta, if these aren't, it only has two values, 0 or 1. If these are not the same as 0, so this is 0, 0. What's this? That's a 1 and a 1. So we get negative 1 equals 0 minus 1. So it does work. It does work, as you can see. My complaint is that it's not obvious that it wasn't offered without what it was offered with no proof. Okay, so let's just swallow our pride and use that. So we want to substitute this back into our equation, which is this, and we get this mess. Okay, let's distribute this, and we get a bigger mess. Now let's break this one out and look at it, okay? Now this part I'm fine with. It made total sense to me. Okay, so we got two Kronecker deltas and our vector components. This whole term can only be non-zero, not equal to zero, if these two are identical, which means that J equals M and K equals N, which makes this J and M and this K and N, right? And this becomes 1 times 1 if that's true. It's likewise for the second term, the exact same thing. This can only be non-zero if K equals M and J equals N, which makes this 1 times 1 times this, the product. So let's put that back in to our equation, and we get this. Now, these are vector components. We can move them around any way we want, okay? And we did, and we get this. Okay, now here comes, it's not a trick, it's just, it's confusing. At this point, we are to recognize that this and this are component forms of the dot product. Okay, because I always think in generalized coordinates, I said, no, that's not actually true. Let's investigate what they're talking about here. Okay, so let's take a vector A and C, which has these linear components, right? Well, when you do the dot product, you know this turns out to be the metric tensor times the components. Okay, let's expand that in 2 dimensions. So we get this expression. Now, in order to make this work, when would A dot C just equal this term and this term? In other words, GNN, AN, CN. That's what they're claiming here, ANCN. When would that be true? Well, that would be true when you have this condition, that the metric tensor is 0 across the diagonal. Well, what does that mean? What's that mean when it's 0 across? It means the basis vectors are orthogonal, right? So E1 dot E2 is 0 and E2 dot E1 is 0. All right. So this instantly makes this proof not true in any coordinate system, right? It makes it true in coordinate systems where the basis vectors are orthogonal. So, I mean, most of the 95% of the time, I'm going to say you're probably doing cross products in Cartesian basis vectors anyway. So, anyway, it's just a pet peeve of mine. It's just not true that that's the way it is. Okay, so anyway, back to the story. It sounds like I'm complaining a lot, doesn't it? So we have this expression. Now remember from the beginning. So we said, here was the expression we had, and we said B cross C is D. We put D in there. And then we said A cross D is G, remember? So we have now this expression. So this is saying that the components of this vector G is equal to the components of B times this dot product, which only works in orthogonal coordinate systems, minus these components times these this component of this vector times this dot product. Okay, so I mean it does work. It's limited to what you can do with it, but it does work. Now that's the reason I didn't offer this as a problem of the day, because I think it's too wacky. Anyway, thanks for watching. See you later.